What are 3D coordinate transformations in robot kinematics? Imagine trying to tell a robot exactly where to move its arm or end effector in space. To do this accurately, the robot needs a way to understand positions and orientations in 3 dimensions. That's where 3D coordinate transformations come into play. They are the mathematical tools that help convert the position and orientation of points or parts from one coordinate system to another within 3-dimensional space. Think of it like translating a location from one map to another, but in a way that also accounts for how things are rotated or shifted. These transformations are vital for controlling robotic arms, joints, and tools, especially when they need to work precisely relative to a fixed base or a moving part. In robot kinematics, the 2 main operations involved are rotation and translation. Rotation changes the orientation of a coordinate frame by turning it around one or more axes. This is represented by a rotation matrix, which is a 3x3 grid of numbers that describes how the axes are aligned after rotation. Translation, on the other hand, shifts the origin of the coordinate frame by a certain distance in 3-dimensional space, which is represented by a displacement vector. When you combine rotation and translation, you get a powerful way to describe how one coordinate system relates to another. To make these combined operations easier and more efficient, engineers use homogeneous transformation matrices. These are 4x4 matrices that blend the rotation matrix and the translation vector into a single operation. When you multiply a point's coordinates by this matrix, it converts the point from one frame to another, keeping track of both its position and orientation at the same time. This process is essential for forward kinematics, where you calculate the position of the robot's end effector based on joint angles. It is also used in inverse kinematics, where you work backwards to find the joint parameters needed to reach a specific point. From an electrical engineering perspective, understanding these transformations is key for designing control systems. Sensors like cameras or LIDAR gather data in their own coordinate frames. To interpret this data correctly, the system must convert it into a common reference frame. This allows the robot to process environmental information accurately and plan its movements. Signal processing techniques often relying on these transformations to analyze sensor data and generate motion commands. In practical terms, these transformations enable robots to navigate autonomously, manipulate objects, and coordinate complex tasks. For example, in manufacturing, robotic arms use real-time coordinate transformations to position tools precisely. In autonomous vehicles, sensor data must be transformed into a unified frame to understand surroundings and make safe decisions. Overall, 3D coordinate transformations form the backbone of how robots understand and move through their environment, ensuring they perform tasks with accuracy and consistency.